Now, yesterday we looked at vertical asymptotes, and we're going to incorporate that work at the end of this example. But first of all, horizontal and oblique asymptotes. What we have here is an improper rational function, because the power of x on the bottom is the same as the power of x on the top. That's to say the highest power of x. So we're going to have to carry out a simple division. You did one of these recently. So x then dividing into x minus 3. What do we multiply this x by? To get this x here we multiply by 1. So 1 times x is x. Subtract. So x take away x is 0. Minus 3 take away 0 is minus 3. What does that mean? It means that we can write this function as 1 minus 3 over x. Now, let's just forget for a minute about the minus 3 over x. We've got a constant here, y equals 1. The line y equals 1 is a horizontal line. This then is the equation of the horizontal asymptote. Y equals 1. Now what we have to do is to work out how the graph behaves around about this asymptote, this horizontal asymptote, y equals 1. Now it's nice and simple because this part of the function is very easy to use. What we're going to do then is to consider x tending to positive infinity. So we're very large positive values of x. Now, this whole term here is negative. So if I have a very large positive value on the bottom, what I end up with is a very small negative value, which is to say y tends to 1 minus. When x is very large and positive, the function has a value which is just less than 1. So let's do that again. This whole term here is negative because of the negative. So if I put a large positive value here, we get a small negative number. So it's 1 take away a little bit, which is to say something just less than 1. So if I was to just, as we did yesterday, here is our horizontal asymptote at y equals 1. So for very large positive values of x, which is to say x in this direction here, the function tends to 1 minus, which is to say the curve approaches y equals 1 from below. Now, as x tends to minus infinity, so we've got a very large negative value. Well, the negative of our large value here and this negative cancel out. So we end up with a very small positive value, 1 plus. Which is to say, as we travel in this direction here, the function tends to y equals 1 from above. Now we've dealt with the horizontal asymptote. I'm sure you remarked on the fact that we've got an x on the bottom line here. So we might very well see a restriction on the domain, like so, x cannot equal 0, which is to say we have a vertical asymptote at x equals 0. And it would be useful, in fact essential, to see what happens on either side of this vertical asymptote. So as x tends to 0 from the right, what happens? So if we've got a very small, positive value, we put it in here. So 3 divided by a very small positive value gives us a very large positive value. So 1 then, take away a very large positive value, gives us a large negative value, which is to say, as we get closer to the horizontal asymptote, here's a horizontal asymptote at x equals 0. So to the right of x equals 0, y tends to negative infinity. And as x tends to 0 minus, I hope you can see that y tends to positive infinity. Let's just check that. So we've got a very small negative value, say something like minus 0.1. Well, this is already a negative, so these two negatives are going to cancel. We're going to have 1 plus a very large value. So 3 divided by a small value is a large value, and the negatives cancel. That means that we have something that looks like this. What I want to do here is to bring together the information which we have discovered about this function. So when x tends to positive infinity, we had a shape like that, and when we're very close to 0 from the right, we have a shape like that. When x tends to negative infinity, our graph does something like so, and when x is very close to 0 from the left hand side, we have something like so. Now, there's only one thing that can happen here, and these branches of the curve join up like so. Here's a second example, and this one's slightly different from the first one. Notice again that we have x squared on top and x on the bottom. So we have an improper rational function. We have to carry out a division. X minus 3 dividing into x squared plus 5. So what do I multiply x by to get x squared? I multiply by x. X times x is x squared. X times minus 3 is minus 3x. We'll subtract. So x squared, take away x squared is 0. 0x minus minus 3 gives us 3x plus 5. Now, we have to continue this. Here we have x to the power of 1. Here we have another x to the power of 1. So we must carry out the division again. What do I multiply this x by to get 3x? I multiply by 3. 3 times x is 3x. 3 times minus 3 is minus 9. Subtract. 3x take away 3x is 0. 5 minus minus 9 is 14. So what I have then is that y equals x plus 3 plus 14 over x minus 3. Now, this here is the asymptote. That's not a vertical asymptote, and it's not a horizontal asymptote. This is what we call an oblique asymptote. The line y equals x plus 3 is a line which looks like this here. And what we're going to do now is to find out what happens as x tends to positive and negative infinity. So as x tends to positive infinity, let's look at this term here. This is nice and easy to work with. So a very large positive value, take away 3, is still a large positive value. 14 divided by a very large positive value is small and positive. What that means is that y tends to x plus 3 from above. So we've got x plus 3 and a little bit. As x tends to negative infinity, y tends to x plus 3 from below. Let's just check that. So we've got a very large negative value. Now the minus 3 is, to all intents and purposes, irrelevant here because this value is very, very large. So we've got 14 over a very large negative value. That gives us a very small negative. So it's y equals x plus 3, take away a small amount, hence the negative here. So if I sketch in my oblique line, which has equation y equals x plus 3. So for large positive values, we're above y equals x plus 3. Large positive values are in this direction. Large negative values are in this direction. So as we move to the left in our diagram, we're approaching the line y equals x plus 3 from below. What I'd also like to do is to look at the vertical asymptote, because you can see that we cannot have the value 3. So we've got a vertical asymptote at x equals 3. Now what happens as x tends to 3 from above? So we have, say, 3.1. 3.1 take away 3 is 0.1. We've got a very small positive value on the bottom. So 14 divided by a very small positive value is a very large positive value. In fact, it's so large that that term dominates. So this is irrelevant, which is to say we're heading for positive infinity. So to the right of x equals 3, y tends to positive infinity. And when x tends to 3 from the left, y will tend to, well, it's going to be negative infinity. Let's just check that. So 2.9, say, 2.9 take away 3 is a small negative value. So 14 divided by a very, very small negative value gives us a very large negative value. It's so large that it dominates this, which is to say we're tending to negative infinity. If I draw in my vertical asymptote at x equals 3, so to the right of 3 we've got a very large positive value of y, and to the left of 3 you've got a very large negative value of y. So I'm going to tie these things together as best I can. We've got the non-vertical asymptote, which is to say an oblique asymptote with equation y equals x plus 3, and we have the vertical asymptote with equation x equals 3. Now we have something like this and like this, and if you go back to slide 5, you can see that we also have something like this and like this. And the only thing that can happen is that these join up. It looks very much as though that we have a maximum turning point here and a minimum turning point here, but that will be for the future.